Welcome to Embedded Development with the Zybo board. In this video, we'll be putting embedded Linux on the Zybo board and booting off an SD card. I've used quite a few resources. They include the video series by Tom Briggs on YouTube. Check them out. Also go to yoctoproject.org and digilentincorporated.com, or Digilent Inc. has a document on how to do some of this. Put it all together. At the end of this video series, you'll get something like this. You'll be able to plug your micro SD card into the Zybo board, and you will be able to power it up, and you'll be able to access a very small version of Linux that will be running on the Zynq processor. It's recommended you have a terminal or terminal software such as PuTTY or TerraTerm. This can be downloaded. You should be able to configure it using Device Manager and simply plug it into the micro USB port. It's a very lean operating system, so there isn't much here. You're not going to get a GUI or any HDMI output. You're not going to really be able to plug a keyboard into it. That's pretty much what you're going to have. Now, the prerequisites before proceeding, I'd highly recommend having a Zybo board, a micro USB cable, a micro SD card, and some type of micro SD card reader. There's about 10 steps in this process, and we're going to revisit this list repeatedly so you'll know exactly where you are. So just stay tuned and follow along. So the first thing you can do is download Ubuntu Desktop to your computer. It's going to be an ISO or an image file. Download that somewhere safe into a folder and keep track of where you've put it. Also, you can download Virtualbox from their website. Do not forget to get the additional packages. So first download Virtualbox and then download these extensions. So both are important to have installed. So Virtualbox will allow you to run Linux off your machine, your Windows 10 machine. If you happen to be using Windows 10, I'm using Windows 10. Go ahead and after you've installed it, set up a simple system. You can name it whatever you like. You might want to designate it with as much memory as possible. It certainly helps when building the kernel. Now, if you already have a Linux machine, you don't need to use VMbox. I'm just assuming you're probably using Windows. And if you are and you're completely unfamiliar with Linux, then just follow along these steps as you see here. These are the settings that I'm using. So, once you've gotten to this point, you can go ahead and proceed. I've sped up my video. It might take you a few minutes. I think it took me about 8 minutes to do this. Now at this point you should have the Linux ISO on your machine as well as Virtualbox installed and have created a new machine. So next we want to install Ubuntu on the virtual machine. Go ahead and click Start. Now select the location of your image file. So go ahead and go through the Linux installation process and just get Ubuntu running on the virtual machine. And this is just a simple installation, and there's nothing more to it than that. So next we're going to configure the virtual machine hardware, which is basically the SD card reader. This can get a little tricky. Anyway, this is our operating system right now. It's a fresh install. There's nothing in it. I'm going to go ahead and shut it down. So exit Ubuntu. Now you can go to Settings and USB and add a USB 2.0 device. Does not appear to be enumerated at the moment. So we're going to have to plug it in. Now it's tricky. VMbox, as of this video, does not support a USB 3.0 card reader, but it will support a USB 2.0 card reader. So what I'm using is a cable that's designed for USB 2.0. So what will happen is when I plug the card reader into the PC through the cable, it will be enumerated as a USB 3.0 device, but it's only going to work as a USB 2.0 device. So in VMbox, under USB configuration, add hardware for a USB 2.0. Otherwise, you may get errors. I did get errors until changing this back to USB 2.0. And it is enumerated here as a 3.0 card reader, but it is selected as a 2.0 USB device. Go ahead and start the virtual machine. And once your virtual machine is up, you can explore the file system. Now I'm going to use an SD card that already has the entire embedded Linux distribution on it. And this will give you a little insight into some of the files that are going to be needed to put onto the SD card. We'll cover that again later. And I'll show you exactly how to do that. And that is a little bit toward the end of this video. So you can use the ls-blk command. This shows you whether anything's plugged into your virtual machine or recognized by Linux. So we're going to plug in the micro SD card into the reader. Now before it was not recognized. Now if we run df or ls-blk again in the console, there should be a difference. Now this card has already been formatted, so when it's plugged in, it's immediately recognized by the operating system. This is the file structure on your root FS on the left. On the right, you have the ZedBoot. There's about 6 files in ZedBoot, actually 7. You will need all of these files installed on your micro SD card. And we're going to cover that. We're going to go over that step by step as we progress through this video. Of course, we have to build the kernel first. You have a boot.bin, you have a uboot file, you've got a uimage. This file, uemv.txt, needs to be edited so that it points to the correct files in your boot partition on the SD card. So again, we'll cover that when we get to that step, so don't worry about it too much right now, but just be aware that essentially that's what we're going to be doing, is we're compiling an entire Linux kernel using a toolchain called Yocto, and the toolchain is going to create a series of files that we need to put on the SD card in special places. This is a list here. We have boot.bin, core image, there's stuff. It's a uboot extension, we'll get into that. Uboot image, uenv.txt, uimage, and so on, and a root file system as well. And they need to be put into their own partitions, which means their own sections on the SD card. And again, we'll cover that shortly when we get to it. So here we've used the ls-blk command, and notice our SDB under name, when it's mounted, it's under the mount point column, and under media, ePraxis, and a name, ZedBoot and root FS. So use the ls block to list where it is located. So we're unmounting it with these commands. We want to unmount these disks before we pull it out of the SD card reader. So we've unmounted the media, and you can run ls-blk again, and you'll notice there's nothing mounted. Also df, if you're unsure whether it's mounted to your SDB port, you can just run those commands to verify. Anyway, so what I'm doing here is taking that SD card with that file system installed and putting it into the Zybo SD slot and plugging it in. So if you have teraterm or putty, configure that to work as a COM port, as a COM terminal. You can find out which COM port it is by looking in Device Manager. Under COM ports, it should come up. Here it is COM port 5, and set it to your pretty much default settings for the COM port at 115200 is your baud rate, and let it boot up. So you may not see any activity initially. The loading screen has already happened. Well, loading screen will show you in a moment in the terminal, but you can enter a little bit of data, hit a few keystrokes, you should get some action coming back. So what is the password to your board? I don't know. It doesn't have a password, but it does have a login. If you type in root, it will get you right in. And you can explore the file system. And this is what you will end up with by the end of this video. We can hit reset and watch it load. And this is what you will see upon hitting reset. So again, this is just a preview of what you'll see. Now, I've been through this process twice, and the results are consistent just by following the steps. You'll get something like this. You'll be able to ping your local network. With a loopback. Now you can try to ping your local network, but it won't work unless you plug in the Ethernet cable. So plug that in and you'll see some activity on the Ethernet. And it has been enumerated by the Zybo board. So your link is up and you can just start pinging whatever you like at this point. There's the router responding to a ping. Control Z will stop this if you don't know. If you didn't know, just left Control and Z at the same time will get you out of a process like that. Otherwise, it'll continue indefinitely. We are pinging a Google server. There's our DNS also working. So there's quite a bit of functionality in this system already. It's pretty bare bones. What it doesn't have is it does not have the ability to compile. You can't run a makefile or anything like that, unfortunately. These are some of the other commands you can do. So the next thing that needs to be done is installing the Yocto packages before we can deal with any of the cloning of the GitHub sources or editing any files or any of that. So let's go ahead and install the Yocto packages. This will allow you to build the kernel, fire up your Linux on the VM box. Now there's a few commands that you will have to enter into the terminal or console. I'd recommend going to the Yocto project website. Using a browser from your virtual machine, it's easier to cut and paste. Cutting and pasting is going to be done to get the system ready. So before Yocto can really function at all, it needs some prerequisite software installed. And that's what we're going to do right now. So go to their yoctoproject.org documentation, open it up. And here you're going to find the required dependencies for Ubuntu right here using the apt-get. Now I'm just copying this entire line and pasting it into the terminal. You can open the terminal with Control-Alt-T. We'll bring it right up. It's a shortcut. Control-Alt and T. Right-click, click Paste. Don't forget your password and hit Enter, and you will be able to install the dependencies for Yocto. Okay, now that the dependencies are installed, you can install Yocto itself. So I'm just sort of scrolling down this Yocto project document, and I'm going to copy this line here from the Yocto project release. Copy that, paste it, and hit enter. We're going to git clone the Yocto project under Poky, P-O-K-Y. Just go ahead and do that. We're cloning this entire repository. Okay, we have installed the dependencies and we've installed the Yocto package, or well, we've cloned the project anyway onto our virtual machine. Now we need to clone 2 more projects off GitHub. They are meta-xilinx and meta-openembedded. First, we can explore what we've got a little bit. We can change our directory to Pocky, and you'll see all these files in there. So where exactly is our ARM stuff? Well, we're going to put that on now. So there's two projects on GitHub. One is meta-xilinx and the other is meta-openembedded. And these 2 GitHub projects need to be cloned onto our virtual machine. I'm going to show you how to do that. These are 2 separate Gits. Now this is meta-xilinx. And there are different branches. Branches are kind of like versions. You'll get a branch called master, and you don't want to use that branch. Instead, use one with one of these interesting looking names. We can see that our board is supported under meta-xilinx. If you can just scroll down on the information page, you'll see the supported processors. Now, I made the mistake of initially building this with the master branch, and that was a big mistake because it did not compile. But it did take an hour before it told me it wasn't going to compile. So what I am going to do is go with the Rocco branch. Now, if you're watching this and maybe it's 2019 or 2020 or maybe some other time way in the future, you're going to have to pick a branch that is no one working. It will compile. So just go to the website here and look under their branches and see what they have. See what the latest active branch is. Here we have Rocky or Rocco. So it will be Rocco. So when you clone this Git repository, you're going to use Rocco to refer to this specific branch in both the meta-xilinx Git and meta-openembedded Git. So these are 2 separate Gits, 2 separate clones. If the versions don't match, this is not going to work. So we just type this, git clone-b Rocco, and the address of the Git repository. And the path. So notice we have a meta-xilinx folder in the Pocky directory. It's been created, and you're going to need to verify that exists. Just look in your Pocky directory, it should be there. So the next thing we're going to add is the meta-openembedded. Google search it for where it's located on the internet, on GitHub. Again, I'm using a browser that is inside the virtual machine, just easier to cut and paste, though not necessarily necessary. It's a little bit easier to navigate around and so on. So this is could be the open embedded Git. I'm not sure. There's a few, so you may have to look around a little bit. It will be the meta-openembedded. So click on that one, and that will take you to where you need to be. And this is it here. So again, you're going to need the same branch that you used with meta-xilinx. If they're not the same, this ain't gonna work. So again, it will be Rocco. Now you'll see other sources, videos, or tutorials that advocate maybe some other version that may or may not be current. But as of the date today, it's going to be Rocco. So git clone-b Rocco HTTPS and the GitHub address. And it is cloning. So you want to notice or verify that the file has actually been added. So we do have a meta-openembedded with a little ls list the files in the directory. If you're not familiar with Linux, ls will list your files. Let's go ahead and take a look in the meta-openembedded. These are the files we have. We have more meta layers. Let's go ahead and back out of that and look in the meta-xilinx. And we have meta layers here. Now, if you go into one of the BSPs, one of these meta layers, you'll see recipes, and Yocto works on a system based on recipes. You can read through the Yocto documentation if you want more information about that. We will not delve into that in this video. We're just going to get a little Linux kernel running on the Zybo board here. Git checkout Rocco, so that's going to set up to keep track of the branch. If any changes are made, you'll be notified. So now we have our Yocto meta-xilinx and openembedded gets cloned on the machine, effectively installed, and the next thing we need to do is edit a couple files. There will be local.conf and bblayers.conf. These are configuration files. Local.conf is going to be in your Pocky build conf directory. You can invoke the shell for building the target by typing oe-init-build.env. I'll get you into the build environment. Let's go ahead and look at local.conf. Now, the whole purpose of editing this file is to tell the toolchain which machine to compile for. So we're going to compile for the Zynq7000 series, but not only that, specifically for the Zybo board. So it won't just be for any random Zynq7000 processor. It'll be for a specific instance of that one on the Zybo board. So there's a board support package for all that, and it's supported, and that support file is found in the meta-xilinx. I'll show you that shortly. But for the Zybo board, you would simply type this line here, Zybo-Zynq7. And what really needs to happen is the line below this needs to be commented out with a hash symbol. And let's get rid of the hash that we just put on the line we made. So V is something I'm not very used to. I'm going to be honest. If you hit escape key will escape out of editing. If you want to get into it, you edit where the cursor is. You press A. If you're in edit mode, instead of writing text, if you press DD will get rid of a line. I'll just delete the whole line. Anyway, there's a series of commands to using V. So it's not your normal everyday text editor. It's confusing. It's got two modes. It's got an edit mode and it's got a write text mode. If you're in the edit mode, you can press Shift and the colon key, and press W will write the file. And also in edit mode, Shift colon and Q to quit. So look online to get privy to how to use V. Gedit is a little easier. So there's a location in the meta-xilinx folder that will tell you that you can't actually compile for what we've done. So that line, Zybo-Zynq7, didn't come out of nowhere. It is definitely in the package under meta-xilinx BSP. As it's shown on their website, we can back out of this a little bit, and you'll actually see it on their main web page. We did pass it earlier. So actually on their main page under supported boards and machines, we have the Digilent Zybo, and it tells us right here, use Zybo-Zynq7. So this is what you would write under your machine in that local conf file, as we've done here. And this will compile the kernel for the Zybo board. And that's all we've done here. So that's all you need to edit in this file. That's it. So save this and exit out. So exit out of this. Again, hit escape, Shift colon and W, and repeat that instead of W with Q, and it'll get you out. We want to go ahead and edit the bblayers.conf file using V again, Vi or V or whatever. So next, you want to edit this section here. These are your layers. You can type home dash whatever your user account name is. I've named mine EEPraxis. Just follow what is above, dash Pocky, dash meta-xilinx. So this is not actually going to work, and the reason for that is because the files directly below the ones you're referencing here in BB layers, they need to be recipe files. And you may not remember, but before, the files below, these ones we've referred to, are not recipe files. They're meta files. And I'll show you that in a minute, but we're going to go ahead and enter this anyway, and just to show you what doesn't work. And this doesn't work, and it's an easy point of confusion. Definitely give you a bad day, because it looks like it should work. It looks like the toolchain should go ahead and press down and find where the recipe files are, but it does not do that. So we're in our Pocky directory. So we've typed the meta-openembedded and meta-xilinx into bblayers.conf. Right? Okay, so you can type source oe-init-build-env. This is like an executable file in Windows or DOS or whatever. It's highlighted in green. Anyway, we're in a shell environment for building stuff with the Yocto toolchain. We can type bitbake space core-image-minimal, and this will build our kernel. Well, it's supposed to, if your BB layers file is correct. So this will fail because we have an error in our bblayers.conf file. You'll get an error that looks like this. So we need to go back and edit the bblayers.conf file. So go ahead and get back into your bblayers.conf. Now notice the file structure above. So there are recipe folders that we need to add. One of them is meta-oe that contains a series of recipes. So add that, make sure it's correct. The other is meta-xilinx-bsp, as you saw above. So at this point, we've installed Yocto, the meta-xilinx and meta-openembedded files onto our virtual machine. We've edited the local conf and bblayers.conf. So now we're going to go ahead and run bitbake. So make sure you're in the shell environment and run bitbake core-image-minimal. And this is going to start building the kernel. Now, if you forgot how to enter the shell environment, you do it from the Pocky directory, and you can type source space oe-init-build-env or /oe-init-build-env, and that will get you into this shell environment where you can execute the bitbake command. You can't just run that wherever you feel like. It has to be in this specific shell environment. So right now it's building. This will take approximately, 2 hours. It took me about 2.5 hours. And it will build depending on how many cores you allocated to your system. If it's going too slow, Control Z out. You can Control Z if you forgot to allocate extra cores to your system, your virtual system. You can Control Z to stop this process. Shut down your machine, go to Settings, go to your virtual machine, and edit the system so it uses as many of the processing cores as possible. It will certainly run faster. So we're going to go ahead and do a little movie magic here and speed this process up. I've increased the speed here about 500%. So this has been a long process. Notice only one line is building here. That's only going to build and fetch one thing at a time. This will slow down your build significantly. So what I recommend doing, again, is exit. You can exit with Control Z. It will kill the process. But it's going to save all the progress you've made so far. So you can back out, add 4 processors like this, restart the machine, and open up the terminal, Control-Alt-T. Go back into Pocky, open the shell again, run bitbake core image minimal, and it's going to pick up right where it left off after the parsing of the recipes is finished. And here we have 4 things being processed at the same time instead of 1. Todd points this out in his video. He has an excellent video series, and I highly recommend taking a look at that. So we're building it again just to verify we didn't miss anything. We have 2,475 tasks, of which 2,475 didn't need to be rerun. So if you were to run this command bitbake core image minimal repeatedly, it's not going to start from scratch. It has saved your progress, which is excellent. It's very nice. Otherwise, this process is going to take you about 2 hours or more, maybe a little bit less if you have a fast machine and a fast internet connection. So next we need to put the file system on a micro SD card properly. And that's what we're going to do next now that we've just finished building the kernel. This is an exciting step if you've never done it before, and if you've never done this before, it can be very aggravating if you're unfamiliar with how to mount things in Linux. So you can use the Blk command. This will tell you what is or is not currently recognized by your machine. Now I've just plugged in a blank micro SD card into the card reader. Brand new, completely fresh micro SD card, and it is enumerated under SDB. It says SDB1 is mounted to Media EE Praxis 3764-6433. So before we can do anything, we should unmount that. Also, if you use the df command, you'll also see it's mounted on where it says it is -dev-sdb1. Not only are we going to format and place the correct files on the micro SD card, but we're going to also edit a single file called uenv.txt. Otherwise, this won't work. So first, let's unmount that device. Don't forget your password. So notice it's on SDB, right? And this was the card that we just unmounted that was initially recognized by Linux when we plugged it into the SD card reader. So we're going to use the fdisk command, and it's going to be dev-sdb sdb1. Well, sdb. Doesn't really matter if it's a 1 or not, just write sdb. So we're going to change, and we'll actually format this micro SD card. We're going to create 2 partitions on it. Use the p command. This will tell you which partitions are currently on it, and we have 1 partition which is formatted for a FAT32 file format. So we press D to delete. So this just deleted the partition. If you press P again, you'll notice it's gone. Get a different message. That is missing. It's gone. It's been wiped. If you make a mistake, you can always go back, delete partitions, and repeat this process as many times as you like. If you maybe create extra partitions or format one of the partitions incorrectly, I recommend just go back, delete it. It's only going to take you a few minutes, and start from scratch here. So next, press N. This will create a new partition, P, after you type N. If you type P, it's going to make it a primary. Partition number 1, and you want to use the first sector as the default one, and the last one is +1G. We've entered +1G. Hit enter, and it says we've created a new partition. And if you press P at this point, it will tell you, show you the partition right there. Let's create another one. Press N. It's also going to be a primary partition. We'll press P. Partition number will be 2, and it's just going to be the default value, so you can just hit enter and enter. Okay. If you press P again at this point, you'll see both partitions here, dev-sdb1, and we also have dev-sdb2. If you press W, it's going to write the partitions. Next, we want to make a file system. Sudo mkfs-t vfat-f16-n, and just give it a name, ZedBoot. And it's going to be on dev-sdb1. Now, if you don't type -f16 there, as shown, you're not going to get the correct file system format. It has to be 16. If it's 32, this ain't going to work. Next, we want to format the second partition with makefs-t. It's going to be an ext4. We're going to give it a name as rootfs, and that's going to be our dev-sdb2. So hit enter. If you just type it as shown, you should be okay. If you make a mistake, just go ahead and delete the partitions again and repeat the steps until you get it right. So once it's done writing, you should get a message like this. And we can go ahead and look at our operating system. It will recognize our ZedBoot partition. And it's also going to see our root fs. You can look at properties. Notice it is MS-DOS type, 16 bits. And it's 1.1 gigabytes or so. And our root file system, we can look at the properties, is 13 or so gigabytes free. That's where the file system will go. The first partition was to allow the system to boot up. So we can look around. Let's go into what Yocto had built. Go down this file path, pocky build temp deploy images Zybo-Zynq, and this is everything that was built by Yocto. And some of these files are going to be taken from here and copied onto different portions of the SD card. There's going to be a root file system, and it's contained in the tar.gz up there in red. I don't know if you can see it. It's core-image minimal Zybo Zynq7. It's the second red line down. It's a root file system.tar.gz. That is going to be extracted and copied onto the root fs partition. And there's about 6 other files that are going to go on to the Zybo boot partition. So let's first deal with the root file system here. So go down into the directory here. We can make a temporary directory, temp sd_ext4, and we're going to mount it. So we've created a file system in Linux that's going to have some relationship with the SD card that's mounted on dev sdb2. So remember, the file system for the root file system is ext4. So right now we're trying to put the root file system. This is going to be the bottom item under root, the uncompressed tar generated by Yocto. We are trying to load that into the root file system on the SD card. And we have to uncompress those files from that one file that I showed you into root fs on the SD card. So once again, going down to the directory where the images are contained under pocky build tmp, and down into deploy images and Zybo-Zynq7. So we're trying to copy, let's just go ahead and copy that core image minimal Zybo, rootfs.tar.gz, and don't forget all of those numbers. Now, if you're not familiar with Linux, you can press tab, and it will fill in blanks for you. And we're just going to go ahead and copy that to our directory where the SD card root fs was mounted to, which was tmp-sd_ext4. So that's going to copy the whole zipped or compressed file into that directory. Now if we change directories, to where it's mounted, and you can see where it's mounted using the df command. If we change directories to tmp-sd_ext4, we can run the uncompress command, sudo tar zxf, and just unzip that core image minimal Zybo Zynq, a bunch of numbers .rootfs.tar.gz. So that's been unzipped into this directory, and we can clean it up by deleting the zip file from this directory. Now it's already been unzipped, so we don't need it here, and it is just a copy. It was copied from the Yocto directory under temp deploy images Zybo Zynq. So you can remove a file with the rm command, remove -f to force it to be removed, and it will be the file name. You might want to use sudo rm-f because you need permission to delete stuff. So you want to type sync to make sure the media is synchronized. It's all copied onto your SD card properly, or synchronized with the file system. I'm not really sure what it does. I'm not a Linux expert, but I do know that people type sync quite a bit before unmounting. So unmount temp-sd_ext4 or whatever you named it. So it's not going to unmount unless we get out of the directory we're in. We're in the directory we're trying to unmount. And that's why it's giving us these silly errors, telling us, oh, you cannot do that because the target is busy. Yes, it's busy because the cursor is on the target right now. So just go ahead and exit out of that directory like this. Okay, it looks like we're out. Let's go to home. Let's go back to our Pocky directory. And we can unmount it using sudo umount and where we stored it. So we have our root file system up. It's recognized by Linux. You can explore around. And everything seems to be there. Okay, we're not quite done. We have a couple files that we need to copy onto the Zybo boot partition of the SD card. Otherwise, the root file system is useless at the moment. And notice the ZedBoot. Well, it's not really Zed, it is Zybo. So that's a misnomer. This partition has been misnamed, but that's okay. It's not going to affect us here. You could have called it whatever you wanted. Anyway, it's on dev sdb1. Let's go ahead and make a directory, -p temp sdfat16. It's a FAT16 format. So we're going to mount the ZedBoot partition to this file folder here. SDB1 is going to be mounted to TMP, the SDFAT16. Can run df again, and you'll see it's mounted there. Notice the change. Okay, so there's a list of files that we need to copy over here from the Yocto toolchain directories onto the SD card. One of them is boot.bin, so let's go ahead and copy boot.bin to TMP to our mount point, SDFAT16. And there's a few more files as well. You want uimage. There's no extension on it. It's just uimage. Copy that one over. If we bring up our Linux view of the, well, our windowed view of the file, you can see these files are being copied over. We need this core image minimal.uboot. What's the core image minimal? Zybo Zynq 2018 622519 numbers, etc. Your numbers are going to be different, but you're going to get a file that is similar to that. It's going to be a u-boot file. So copy that over. So we have 3 files so far, and we need 3 more. You want to copy over uenv.txt. This file is going to be edited, or it may be edited. We'll see. Maybe not. But in any case, you want to read that file. It will give you a hint at the other files you need on the boot partition. Copy over the DTB extension file, CPU image-sync-zybo.dtb. Copy that over. You might have a DTA or a DTC or DTD extension. It will be a little different, but it's still going to be the uimage-sync-zybo dot whatever extension it is. It's a DT file. So this file name corresponds to a file name referenced in uenv.txt. Environment, could it be? I'm not sure. And I'll show you that in a moment. And you're also going to want the u-boot.img. And that will be the 6th file. So you'll have 4 files total. So if we edit the u-env.txt file, you'll see a reference to Zynq-Zybo, while the u-image-Zynq-Zybo.dtb. So that's referenced here. So if you don't know which dt whatever file to use, you can find out which one it is here in the u-environment.txt file here. If you don't know which kernel image is being referenced, you can look here at ui-image. You can change these if you want. I'm not sure what effects those will have, but try doing this first and getting your board to boot up. So let's go ahead and unmount what we have so far. Just go ahead and unmount everything after those 6 files are copied over to your boot partition and your other files have been copied over or extracted to your root file system. Just go ahead and unmount both. So at this point, we've completed the first 9 steps, and there's one final step, which is simply putting the micro SD card in the Zybo board, connecting it to one of your terminal applications. If you have PuTTY, MobaXterm is another application. And just set it for serial. And whatever COM port that you happen to be using. Mine is 5. When I plug in my Zybo board, it's enumerated on COM port 5 in Device Manager. The speed is 115200. Fire it up. And again, it doesn't have a password, but it does have a login name, which is going to be root. And we can explore the file system here. So just for your reference, if we take it out of the Zybo board, plug it back into Linux, you can take a look at both files, both partitions on the micro SD card and also the uenv.txt file. It should look similar to this. These are the files you need. Make notes. If you aren't using the right files in the boot partition, it's not going to work. So once again, for your convenience, the files that will be copied over So remember, this Linux system is very minimal. You're not going to be able to compile anything on the processor. It doesn't have any compiler installed. You can't run any makefiles. This is a bare bones minimal build. Anyway, thank you for watching. In the next video, we're going to put a custom embedded Linux driver for the programmable logic into the kernel. So we'll be able to interact with our programmable logic on the Zynq chip. Once again, thanks for watching, and I hope to see you there.